For the electronic valve instrument I'm building, I need a way of translating thumb movements into an electrical signal that can control musical vibrato. To do this, I decided to use a Hall effect sensor. Some interesting physics and maths came up along the way, so I'll be sharing those with you today. Without further ado, let's dive into a little physics. To understand the Hall effect, we first need to know about something called the Lorentz Force. This force acts on charged particles like electrons when they move through a magnetic field. It comes up in a number of different situations in real life. For example, in a cathode ray tube TV, it's exploited to steer the electron beam across the phosphorescent coating on the back of the screen. For any zoomers out there watching who've never seen one before, this monstrosity is a CRT. The equation that describes the Lorentz force is this thing here. Note that the letters in bold are vectors, meaning they have a size and a direction. Vectors are often used to describe physical phenomena like forces, fields, and velocities and other properties where it's not just the size that matters. First we have the force itself on the left, then the charge of the particle we're looking at. In our case this will be an electron. Next we have the electric field that the particle is currently in, and after that there's the velocity. Remember that velocity is the vector equivalent of speed. Speed is a scalar and therefore has no direction specified. Finally on the right, we have the magnetic flux density, which is just a fancy way of saying the magnetic field strength.
But why is the symbol B?
I hear you ask. Well, it's because the unit for magnetic flux density is Tesla, and we all know that Tesla starts with a B. We can simplify this equation a little bit, as we're not actually going to be needing the electric field for what we're looking at. That leaves us with this. But what's that cross thing at the end before the B? Well, that's the vector cross product. And what is the vector cross product? You're about to find out. The cross product is just another mathematical operation like multiplication, addition, or division, but instead of being applied to scalars, which is just a fancy way of referring to the normal numbers we use to count, it's used on vectors. The cross product of two vectors a and b produces a third vector perpendicular to the first two, which I'm calling c. I find the easiest way to imagine this is to think of the first two vectors as lying on a plane, and the third standing straight up from it. If you don't care about the direction, or you know what it is already because you know it's poking off the surface of a plane, calculating the magnitude of vector c is pretty easy. You just need to multiply the magnitudes, the sizes, of a and b, and the sine of the angle between them. The effect of this is that if you make one of the vectors smaller or bigger, the magnitude of the cross product changes accordingly. Similarly, changing the angle between a and b changes the magnitude of vector c. The magnitude is at a maximum therefore when the angle between a and b is 90 degrees. Though the cross product symbol is sometimes used in scalar maths to mean multiplication, properties are slightly different for vectors. For example, the cross product is not commutative, meaning that if you reverse the order and do b cross a instead of a cross b, you get a different resulting vector c. In fact, you get the same magnitude of vector, but with the opposite direction. Calculating the full vector is a little harder if you want the direction and the magnitude. You use something called a matrix determinant, which is a little beyond the scope of this video. The vectors I, j, and k here are just unit vectors, or vectors with a magnitude of 1 that point in the same direction as the x, y, and z axes. I've put the expanded form of the matrix determinant here, in case you want to use it as just a plug-in formula. At this point it's probably good to bring up the right hand rule. Using your right hand, your index finger represents vector A, middle finger represents B, and your thumb is vector C. This is a pretty common way of remembering which way round things go, so if you see engineers in an exam throwing gang signs, you really need not be alarmed. If we take a step back and look at the Lorentz force again, we can map these vectors onto a hand. Note that current is just a physical flow of charge, so it's in the same direction as the velocity. First we have the current on my index finger, the magnetic field on the middle finger, and finally the force produced on my thumb. Simple? Well, actually there's a little problem here, and it's with that scalar q for charge. As you might already know, electrons have a negative charge. What I'm showing on my hand here is actually the case of conventional current, which is the opposite of the direction that electrons actually flow. Conventional current flows from positive to negative potential, while electrons flow from negative to positive. Engineers usually use conventional current because it works out nicely with positive and negative signs in equations, but for physics it can be helpful to look at the more correct electron current. As we'll be using electron current to explain the Hall effect in a minute, I'm going to swap over and use my left hand, which is an easy way of swapping the direction of the current vector. When you've been doing vector maths long enough, you might find that you've actually become flexible enough to do the right hand rule with your left hand. I always recommend stretching a bit before trying this though. Wouldn't want to pull a muscle. Now that we've got Lorentz firmly tucked under our belt, we can have a look at the Hall effect. To start off with, we'll hook up a chunk of some semiconductor, perhaps gallium arsenide, to a battery so that we can pass a current through it. As there's no external magnetic field acting on it at the moment, the electrons tend to flow on average in a straight line across the semiconductor. As a side note, remember that I'm using electron current here, not conventional current. If we now apply a magnetic field across the chunk of semiconductor, the Lorentz force comes into play. Instead of shooting straight across, ignoring a bit of bumping into atoms along the way, the electrons are forced over to one side. To work out the direction they're going to go, we whip out our left hand, and lo and behold, they're going to the left. Because the electrons are being pushed to one side, we end up with a higher concentration of negative charge there. Whenever you have a difference in charge between 2 points, you get an electric field. At this point, if we take a voltmeter and hook it up from the negative side to the other side, which is now positive relative to the electrony side, we can measure a voltage, which, in theory, we could use to drive a current. While this is a simplified way of explaining the Hall effect, it does cover the main points. In practice, Hall effect sensors like the A1301 that I'm using for my electronic valve instrument project have a bunch of other stuff inside their packages, like amplifiers and filters, to make up for the fact that the Hall effect alone would not be strong enough to drive an external circuit. On that note, that brings our video to a close. I hope you learned something. I'll leave some links in the description to other examples of the cross-product's usefulness and some examples of the Lorentz force. Make sure you subscribe so you don't miss the next video where I'll be showing you how I use a Hall effect sensor to build a vibrato system for the electronic valve instrument I'm building. As always, stay safe and have a great day.